Okay, so part B, we're still in 4.3, trying to learn some applications for word problems, trying to figure out where would we use some of this information that we're learning, right? Okay, so what I'd like you to do, if you have your calculator readily available, do me a favor, see if you can find the following buttons on your calculator. So this is going to, I'm going to knock out the next two problems, but I want to make sure you understand something. This is going to seem a little bit gimmicky because section 4.7 deals with inverse trig functions in great detail. So if you allow me, I'm going to show you how to use these buttons on your calculator, but then I'm going to punt on the elaboration of what is an inverse trig function until we get to I believe it's 4.7. Okay? So as of now, here's all I need you to know. So of course, sine of theta, right, that gives you the ratio opposite divided by the hypotenuse. But this button, this is called sine inverse or arc sine. If you use this button, what comes back out is the angle. I'm going to say that one more time. If you want to know the angle, right? The last two problems we already had the angle. We didn't want to know those. We didn't need to know that. But if you are trying to find the angle, these are the buttons that you want to use. Okay, these are your inverse. And I'm going to jump in without the explanation until we get to a later section. So let me read the question. It says, so a building that is 21 meters tall casts a shadow 25 meters long. Okay, so I like pictures, so I'm going to go ahead and draw this out. So this is my building. It's 21 meters tall, and it looks like it casts a shadow. All right, so we'll say our sun's over here. Look at this beautiful sun. Look at this. All right, casts a shadow, and if you were to measure that shadow, it's going to be 25 meters long. All right, so far so good. Let's get back to the question. So we want to find the angle of elevation of the sun to the nearest degree. Now, interesting, really quickly, because I've seen students go wrong on this. So of course, we know that this is the 90-degree angle. The question is, are we looking at this angle or are we looking at this angle? Because it matters, right? Because 21 is opposite to this angle, but 25 is the opposite side to this angle. So we need to know which angle we're looking at. So the key thing here is find the angle of elevation. Remember, elevation, you're looking up, right? So this can't be the angle of elevation, right? This would be the angle of depression. So it has to be this one. So this is our angle that we're interested in. All right. So I'm gonna do exactly what I said I would do. So I'm gonna list what I have. I'm gonna list what I need. And let's go ahead and start with what we need. So do you agree with me? The thing that we don't have is theta. Right? That's what we want. We don't have the angle. But we do have what? Well, we definitely don't have the hypotenuse. But we do have the opposite. Right? So the opposite to here is 21. And we do have the adjacent. So adjacent to that angle is 25. All right. Well, it looks like tangent's going to win out again. So notice that tan of theta is equal to opposite over adjacent. All right, I know what to plug in for adjacent. I know what to plug in for opposite. Only stick with me here, because we need to somehow, something has to trigger, right? That we're going to use not tan, but tan inverse. So let's plug everything in. So tangent of some angle, that's what we don't have, is equal to opposite, which is 21, over adjacent, which is 25. Okay. So because we're trying to find the angle, right? Tangent of some angle equals 21 over 25. To do that, we use tan inverse. Let me erase that, and I'm going to draw this a little bit more clear. Ready? So tan inverse, this is the button that we want. Remember I said that the inverse buttons, they give us theta. But what goes in here? Well, easy enough. It's just the 21 over 25. All right, so at this stage, you just grab your calculator. As long as you can find access to your tan inverse button, tan inverse of 21 over 25. We're just being approximate here. So I'm getting, if you have it in degree mode, I'm getting 40 degrees, roughly. If you're not getting 40, you might have it in radian mode, okay? Okay, so let's go to the last question of this section, and the last one, save the best for last. So actually, I don't need to go into great detail here about cofunctions. This is more or less so you can get through your homework. So just so you understand, let's revisit some geometry here. So do you remember what complementary angles are? Well, it's very simple. It's just two angles that add up to be 90 degrees, right? So, for example, 70 degrees and 20 degrees, those are complementary angles. Now, the idea of cofunctions, I tell you what, try something for me, if you will. If you have access to your calculator, try something. It'll be worth it. Try taking sine of 70 degrees and then take cosine of 20 degrees. I'll wait. Take sine of one of these and cosine of the other. Doesn't matter which. Take sine of 70, cosine of 20 on your calculator. You're getting the same thing, right? So this is what they mean by cofunctions. And without a long elaboration of the theory here, it's pretty simple. So all the angles of a triangle have to add up to be 180, right? If this wasn't an online class, if we were in the classroom like I normally teach, I'd give you a few proofs. But because this is in video fashion, if you add up the three angles of any triangle, it has to add up to be 180. Now, if you know that one of your angles is 90, then that means the other two have to add up to what? These two right here have to add up to be 90, right? Because 90 and 90 is 180. So all that means is if you know this theta, then this angle must be 90 minus theta. And that's what's happening here. So sine of theta is always going to be equal to cosine of 90 minus theta. Okay, so actually, just as an aside, the word cosine means the complementary, right? The complement of sine. All right. So last question, and it's the best one. Now you can tell from just this, well, you can tell from the question itself how old of a textbook I grabbed this question from. Ready? So it says, in the late 1950s, the Soviets labored to develop a missile that could stop the U-2 spy plane. Right? So here's our U-2 spy plane. Now, so May 1st, 1960, Khrushchev announced to the world that the Soviets had shot down France's Gary Powers while Powers was photographing the Soviet Union from this U-2 spy plane. Okay? Now, Powers was at an altitude of 14 miles. So 14 miles was the altitude. All right. So from 14 miles, now the question is, so from, just imagine that you're up here, you're 14 miles in altitude in this spy plane. From this high, how wide of a path on the Earth's surface could Powers see from that altitude? All right. So now this question assumes that you subscribed to a spherical Earth, right? So that is not as common as it once was, but so you have to subscribe to some type of curvature here in order for this to make sense. But the question is very simple. So from 14 miles up, you can imagine that your plane is photographing, and what we'll assume is that it can take photographs from behind as well as in front. And when it says how wide of a path on the Earth's surface could Powers see, what they're really asking is how this distance here, this arc length, how wide of a path along the surface of the Earth, how much could be photographed from that altitude? Okay. So interesting question, not an easy one. So let's start. They want us to use 3,950 miles for the radius of the Earth. I'll go ahead and we'll just, obviously it's not drawn to scale, but we'll let this yellow dot be the center, and we got 3,950 miles to the surface, right? So 3,950 miles here as well as here. Okay. Now, the last thing I want to draw here is so at this particular point here, this would also be 3,950 miles. All right. The problem is we don't spot any right angle. Where is the right angle here to make all of this work? Okay. Well, let me kind of draw bear with me here. So this is going to be the path that could be photographed. Okay, so there's one little piece of information that came out of your high school geometry class that you would need in order to make sense of this question. So let me draw where the right angles are, and then I'll tell you why. Okay? So the right angles are here, and I can't draw it very well, here. Now, why? So since the picture's not great, but the idea is, let me see if I can help you out here. So the reason why I get to draw those right angles is there's a little property from geometry that says that any line, right? So this is horrible. Any line that runs tangent to a circle is perpendicular to the radius of the circle at the point of tangency. So what that means is, notice how, although it's not drawn very well, notice how I have a line that just touches the circle once, right? Just that line is perpendicular to the radius at the point of tangency. So that's why I get to label my right angles here. Okay, so let's focus on, we have a couple right angles. Let's just focus on this guy. Ready? So what we need right now is we need to know what we have and then what we need, right? So let's list out what do we have. Let's list out what do we need. So first off, the hypotenuse is always directly opposite of the right angle, right? So this is our hypotenuse. So we obviously have to take the 3,950 plus the 14. So in this problem, we do have the hypotenuse. So the hypotenuse is going to be 3,950 plus 14, right? 14 miles in the air. So what is that? That's 3,964 miles. All right. And, well, what else do we have? All right, so, well, maybe let's start with where's the angle? Where's the angle that we're dealing with? So in this case, the angle that we are dealing with is here. So let me ask, do we have the opposite side? Well, no. I mean, that would be this here if we had the opposite side. So we definitely don't have opposite. We have hypotenuse and we have adjacent. And the adjacent is just 3,950. Well, what do we need? Well, think back. In order to find arc length, right? In order to find arc length, let's see if you remember. Do you remember the formula? So S is arc length is equal to R times theta. All right, so we're going to need that viewing angle here, this theta. And let me ask you one more question. Do you remember the little caveat about this angle? This formula, let me just phrase it this way. This formula, does it work for both degrees and radians or only one or the other? Oh, right, this formula only works for radians. So this theta better be in radians or it's not going to work. All right, well, let me finish. What do we need? Well, clearly we need theta. All right. So now you have to imagine yourself staring at your three trig functions, sine, cosine, tangent. Which one of those has hypotenuse, adjacent, and theta? Now, I'm not going to scroll back. You can look back through your notes. But cosine of theta is equal to what? It's equal to adjacent over hypotenuse. All right, now I'm going to go to the next page to give myself a little bit more space. But what I'm going to do is I'm going to rewrite this this formula. But I'm going to go ahead and plug in 3,950 for adjacent, and I'm going to go ahead and plug in 3,964 for hypotenuse. All right, so let's go. So I would have cosine of some angle that I don't know is going to be equal to the adjacent, 3,950, over the hypotenuse, which is 3,964. Okay. Do you remember what we do if we're trying to find theta? Right. We want to make use of cosine inverse. That's how you find angles. So here we go. So cosine inverse is how we get our theta. Now, I'm just going to assume that you still have your calculator in degrees, right? But you could switch it to radians right now if you wanted to and save yourself time. But remember that this is what goes in your function. So 3,950 divided by 3,964. Okay, so cosine inverse of that ratio gives us a theta angle of 4.8 degrees. Now I'm going to go back to the previous page. So the question is 4.8 degrees the viewing angle? Well, this is 4.8 degrees right here. But didn't we say that our spy plane can take pictures both forward and backwards, right? So you would have another angle of 4.8 degrees over here. So I'm going to add those two angles together, but so really your theta is going to be 9.6 degrees. All right. Now, I'm going to go ahead and rewrite that arc length formula. S is equal to R times theta. And in case you've already started daydreaming, or maybe you hear my dogs barking in the background, have you lost sight of what we're even doing? Well, here, you want to know how wide of a path can this airplane take pictures from an altitude of 14 miles, right? I mean, how much of Russia, how many miles, how wide of a path could powers view from that altitude? Well, so we want S. That's an arc length, right? We want to know this distance right here. And all we got to do is, do we know the radius of this circle? Do we know the angle? Well, the radius we're using for here is 3,950. So let's go back over here. So we know that the radius is 3,950. Now, our theta is 9.6 degrees, but you're not going to be that student that falls for that, right? You're not going to put 9.6 degrees here because that's not in radians. So your next thing that you want to do, and I'm not going to review this part, but you want to turn 9.6 degrees, all right, remember you have to multiply by pi over 180, so that's 9.6 degrees pi over 180 degrees. So the degree symbols are going to cancel out. So let me get rid of those. Now, I don't have a calculator in front of me, so I don't know what 9.6 times pi divided by 180 is. But I know that that is the theta that goes in here. Okay? So so the answer is going to be S is equal to R, which is 3,950, multiplied by theta, which is 9.6 pi over 180. So I'm getting an arc length of roughly 661.8 miles. See if you could confirm that. So that is the arc. That is the path that could be seen from that altitude. I will see you in the next section.